Hi guys, today we're back with another graph problem. So we're doing minimum number of vertices to reach all nodes. So we're given a directed acyclic graph with n vertices numbered from 0 to n minus 1 in an array called edges, where edges at I is this, and it represents a directed edge from node this to node this. And they want us to find the smallest set of vertices from which all nodes in the graph are reachable. They say it's guaranteed that a unique solution exists. Notice that you can return the vertices in any order. So if we take a look at the examples, in example 1, we're given this graph where n equals 6, so we have 6 nodes in total. These are our edges, and we would output 0, 3 because it's not possible to reach all the nodes from one single vertex, so we have to use both nodes 0 and 3 to be able to reach all of the nodes in this graph. And if we take a closer look here too, so like this 0, 1 here represents an edge from node 0 to node 1, right? So like it's going from 0 to 1 directed. So as we can see, we have an arrow here pointing from 0 to 1. We have an arrow from 0 to 2 as well, from 2 to 5, right? From 3 to 4, and from 4 to 2. So that's what this represents. In example 2, we have this graph, n equals 5 nodes, and these are our edges, and we would output 0, 2, and 3, because to visit all of the nodes in the graph, we would need to start from 0, 2, and 3. So it's not possible to reach all the nodes if we don't include one of these even. And then, as you can see here, the pattern of which nodes we include is just all of the nodes that don't have any edges pointing towards them. So in this one, right, 0 and 3, there's no edges pointing towards these nodes. In this example, 0, 2, and 3, there's no edges that are pointing towards these nodes either. So if there's nothing pointing towards them, then we need to be able to start from that node to access all of the nodes in the graph. But if there's edges pointing towards a node, so like 1 for example, then we can just reach 1 from one of these other nodes, so we don't need to include that in our final answer. So basically, to do this, we're just going to want to keep track of the in-degrees, which in our edges array is all the numbers at index 1 in these little inside arrays, because if we keep track of the count of the in-degree of each node, then if it's 0, then we'll know that that's one that we need to include in our result, right? So we'll just do this with an array. So like, if we keep track of the index, 2, 3, 4, 5. So like, let's just use example 1, right? We have 5 nodes. Okay, hold on. Then like the indices can represent each of the nodes, because this kind of matches up perfectly with like how many nodes we have, right? And then the number or the value inside of the array for each index can represent the count of that nodes in degrees, right? So for 0, as we can see here, like we'll just loop through this array. So like we'll go through here, we'll check if there's, this is a 1, so we have an in degree for 1. So like, we'll just initialize these all to 0 for now. 0, 1, 2, 3, 4, 5, and then let me make sure that these are lined up as well. Okay, so then like for 1, we'll loop through here and found 1, so we'll increment that to 1. We'll then move on to the next one, check we found a 2, so we know 2 has an in degree of at least 1. Then we'll encounter a 5, so 5 increments. Because remember, these are like, this is like from 0 to 1, so if it's in this position, then that means we know something is pointing towards this node, right? And so every time we find one of those, we're going to increment it in this in degree array. So then we're going to find a 4, so 4 increments to 1, and then we're going to find another 2, so 2 will increment to 2 now, and then this will be our final array because we already like looped through the entire thing, right? So then once we're done with that, we can loop through this array, and if any of these nodes have an in degree of 0, then we know that we're going to need to include it in our final result, because it can't be reached from any other node, right? So then we're going to also need to have, because they want us to return a list of integers, so we're going to have to also keep a list and add each of these nodes with a 0 into the list and just return that. So that should be pretty straightforward. We'll get started. So we'll say int, oops, I somehow turned on my caps lock. Int degree is new int of size n, and they give us n, so we can just directly use it here. Then we're going to want to loop through our edges. So for list of integers, edge in edges. So we're looping through each of these inner arrays right now. That's what this edge is. So we'll say in degree at edge.get1 plus plus, right? So, oops. So, at this edge, this is going to be like here, for example, in the first iteration at least. Then if we get the index 1 in here, that's going to be this value. So then we'll check at in degree, or our array in degree at index 1. The value will be initialized to 0, and then we'll plus plus, so then this will turn into 1, right? And we're just going to do that for every single inner array, every single value, every single value that's inside of these inner arrays, and then we'll do that for that. So then once this loop is done iterating, then we'll basically just have this set up. So then now we need to create our list of integers that we're going to return. So list of integers, let's call it result, is new array list. Then we are going to want to loop through our in degree array. And every time we encounter a 0 here, then we know that whatever index this is, which is representing the node, will need to be included in our result because there's no incoming edges into that node. So for I is 0, I is less than in degree dot length, I plus plus. Then we'll say if in degree at I, so that's going to be this value here. If that is 0, then we're going to want to add that to the result. So result.add I. And we're not adding this value here, we're adding the index because the index is representing the actual node itself. Like, we don't actually care what the in degree is because we're just taking all the ones that have a 0 and we're adding that actual node itself into the array list. So just keep that in mind. So we're just going to do this for every single node in here as well, and then once we're done with that, then our result array list should look like 0, 3, which is what they have here, because we'll loop through here and just check everything that has a 0, and then we'll add the indices for it, which is 0 and 3, and that's just this basically. And then once we're done with that, then we're just going to return the result, and that should be it. So let's test this out. Okay, so now our time complexity. So if we think about what's going on here, so here we are looping through each of the edges to get the in degree. And then for each edge, we are checking one of the nodes that is connected to this edge, right, by doing this part. So that is going to be O of n plus e, where n is the number of nodes and e is the number of edges, because we're doing this for every single edge, and then for a node for every edge. And then in this loop, we are looping through our in degrees, which is storing all of our nodes. This is exactly going to be the matchup to the size of n, which is the number of nodes we have. So this is O of n. And that's basically it. So then this is just going to be, if we add those up, O of n plus e. N is number of nodes, e is number of edges. And then our space complexity. So our only data structures here are this in degree array, which we can clearly see is storing n nodes. And then our resulting array list, which worst case could store n if every single node is like disconnected, I guess, like there's no in degrees to any of them. But regardless, this is still like proportional to n, so if we add these up, n plus n, that still just gives us O of n. And that's it for this problem. Thank you guys for watching, and I'll see you guys next time. Bye!